And let's see. Yeah. So we will cover 3 chapters. The first one is length, area, and volume. The second one will be about some common conversions you will come across as a engineer, also as an operator at working at a refinery. And the third chapter, we will look at a heat and a material balance, and I will show you how to solve simple, let's say, problems. Okay. Okay, so first, length. Definition. Length is a measurement of distance, which is a numerical measurement of how long, wide, or high an object is. The basic SI unit, which means International Systems of Unit of Length, is meter, or short, the abbreviation is M. So normally we express in the metric system everything in meters or kilometers, but in a refinery, we sometimes also come across some other units. So other units often used for length or width. For example, the piping nominal diameter is 1 inch, and 1 inch is equal to 0.0254 meters. When talking about insulation thickness, we will also see that it's often expressed in millimeters, and 1 millimeter is 0.001 meters. Okay. So area and volume. The definition of area is a measure of how much space is on a flat or also two-dimensional surface. And volume is a measure of how much space is enclosed by a three-dimensional object. So down here we can see an example of an area, which is a square. And then the example for volume could be, for example, a cube. So this is two-dimensional, the square, and the cube is three-dimensional. Okay, so let me, okay. So I will just introduce you to some simple formulas, just as a refreshment, of course, I suppose. So how do we calculate the area of a square? So we know that the square, all sides have an equal length. We call it in this example A. So if I want to calculate the area of a square, I multiply A by A, or A square, which if I have a square of 5 meters, the area of that square would be 5 multiplied by 5, which is 25 cubic meters. No, square meters, sorry. The example of a cube with the same length of each side, so 5 meters, and also a cube is characterized by all sides having the same length. So the volume of a cube would be A by the power of 3, or A cubed, which is A multiplied by A multiplied by A. Following the example, the side A is 5 meters. We would have a volume of a cube, of that cube, of 125 cubic meters. Okay. So let us. Okay. So circle and cylinders. So the area of a circle is P multiplied by the radius to the power of 2, or squared. So if we have a cycle with a radius of 5 meters, we would multiply 3.14, which is P, by 5 square, and we will get an area of 78.5 square meters. In the case of a cylinder, the formula for the volume is P multiplied by radius square multiplied by the height of the cylinder. So we assume the radius is 5 meters and the height 10 meters. which would get us at the end a volume of the cylinder of 785 cubic meters. Okay, in the next slide, I will give you one more formula, the one of the sphere. So the formula of the volume of a sphere is 4/3 multiplied by pi multiplied by radius cubed, or to the power of 3. And again, we assume that the radius is 5 meters, and then we apply this formula, and we would get a volume of 523.33 cubic meters. Okay. Okay, now in this chapter, I would also like to introduce you to some metric units, and then on the next slides, we will see imperial units and how to convert between all of them. So the metric system is a quite easy one, and it's the one which is almost used in the majority of countries on the world. So you have 1 kilometer, and if you want to know how much, or 1 kilometer multiplied by 1,000, you will get meters. So 1 kilometer is 1,000 meters. Then if you have 1 meter and you want to know how much centimeters you have, you just multiply by 100. So 1 meter is 100 centimeters. Then again, you have 1 centimeter and you want to know how much millimeters, you just have to multiply your number, or your centimeters, by 10. And then if you go the other way around or go back, it's the same. You just have to divide by that number. So let's say you have 10 millimeters, you divide by 10, then you get 1 centimeter. And it's the same for the other two. It's the same, or it's, 1 centimeter, you divide by 100, you get meters. And when you have 1 meter, you divide by 1,000 and you get the same, or you get the kilometers. So this is pretty easy, pretty straightforward, the conversion in the metric system. Nevertheless, on the next slide, we'll do some examples, okay? So, length. We have 5 kilometers. How much meters do we have? As I already told you, we have seen on the slide before, you need to multiply by 1,000. So 5 multiplied by 1,000, 5,000 meters. So 5 kilometers or 5,000 meters. Centimeters. 120 centimeters, how much meters? Here we have to divide by 100. So 120 divided by 100 is equal to 1.5 meters. So we know 120 centimeters are 1.2 meters. Now, now let's do an example of area where we will see that the equation is a little bit different. So how much, we have 5 square kilometers, and we would like to know how many square meters we have. So we don't have to we don't have to multiply it by just 1,000, but we have to multiply it by 1,000 square, or 1,000 power to the power of 2. So 5 square kilometers are 5 multiplied by 1,000 square, which will get you 5 million square meters. And the conversion with volume follows the same logic. So we have 120 cubic centimeters, and we want to know how much that is in cubic meters. So we don't only have to divide it once by 100, but let's say 3 times, or divide it by 100 cubed. So 120 divided by 100 cubed is equal to 12 multiplied by 10 to the power of minus 5 cubic meter. Okay, so that's the difference between length, area, and volume that you have to take into the account that for area you have to square the division factor, and for the volume you have to cube the division factor, or the conversion factor, sorry. Okay. So in the next slide we will look at the imperial units, which are a little bit more messier. The conversion is not that straightforward. So 1 mile is 1,760 yards. 1 yard are 3 foot. So I have the conversion factor is 3 multiplied by 3. 1 foot are 12 inch. So, and then of course the other way around is 1 inch divided by 12, you get foot. When you have foot, you divide by 3 to get yard. And then if you have yard, you divide by 1,760 to convert to miles. As this is a little bit more, let's say, complicated, or well, not that complicated, but not that easy, or at least normally you need a calculator. It's not that easy to do without a calculator. But let's see some examples. Okay. So 5 foot, and we want to know how much inch we have. So we have to, or we need to multiply by 12. So 5 multiplied by 12 is 60 inch. So 5 foot are 60 inch. 1,000 yards, how much miles do we have? We have to divide by 1,760. So 1,000 divided by 1,760 are 0.568 miles. Area. Remember that when we convert area, we always have to square our conversion factor. Okay, so 5 square foot, how many square inch? We multiply by 12 square, so at the end we have 720 square inch. So 5 square foot are 720 square inch. Volume. So there we have to cube our conversion factor. So 1,000 square yard, how many square miles? We divide by 1,760 cubed, and we will get that, or we will arrive at the conclusion that 1,000 square yard are 1.83 multiplied by 10 to the power of -7 cube miles. Sorry. Okay. In general, I think working as an engineer operator in refineries, you will not come across miles, and also yard is not really used. But as I already told you, inch you do have a lot, because of the diameters of pipes are almost always expressed in inch. And foot is also sometimes used when talking about volumes or volume flows. We will see an example later on. Okay. Now, how do we convert between the metric and to the imperial units and the other way around? So 1 inch is 2.54 centimeters, or when you have 1 centimeter, you have to divide by 2.54 in order to get inch. Conversion between foot and meter is that 1 foot is 0.3048 meter. And then again, if you want to express meter and foot, you divide by the same factor. Okay. Now, yards. 1 yard expressed in meters is 1 yard is 0.9144 meters, or 1 meter you divide by the same factor to get yards. 1 mile is 1.6039 kilometers, okay? And then again, if you want to express kilometers in miles, you have to divide by 1.6093. So again, on the next slide, I will show you some examples. So we have 5-inch, and I would like to know how many centimeters that is. So we have to multiply by 2.54. So 5 multiplied by 2.54 are 12.7 centimeters. 15 kilometers in miles, you need to divide by 1.6093. So 15 divided by 1.6093 is 9.32 miles. Area. Again, remember, we have to cube our conversion factor. So 5 square inch expressed in square centimeters, we need to multiply by 2.54 cubed. So 5 square inch will be 32.258 square centimeters. Volume. So 15 cubic kilometers expressed in cubic miles. What we have to do is we have to divide 15 by 1.6093 cubed, and that will bring us to the solution to have 3.599 cubic miles. Okay. Okay, now we already arrived at the second chapter, which I will present some common conversions you will also most probably will have to deal with when working in a refinery. And the first one is how do I convert between weight fraction and mole fraction? So let us assume that we are given a mixture in mole percent. And then we have to assume a basis for our conversion calculation. So it is very convenient, for example, to assume or to choose that my whole mixture is 100 kilomole, okay? And then we also remember that the sum of all fractions of a mixture of that mixture as well is 1, whether you're working with mole or fractions. So what does that mean? So X is the mass fraction of the ETH component, YE is the mole fraction of the ETH component, N is the number of different components of the mixture. So the sum of the mass fraction of every component in my mixture will be 1. And the same applies to mole fractions. So the sum of all mole fractions, or of the mole fraction of all components, is 1 as well. So with these two assumptions, that the mass fractions and the mole fractions, the sum is 1, and then also that I assume that my mixture is 100 kilomole, with these two assumptions, I can go on and convert from weight to mole fraction and the other way around. So let's look at an example. And in this example, we will convert mole to mass. Okay. So our example is that a gas is composed of 15% carbon dioxide, 20% water, 40% oxygen, and 20% nitrogen, all expressed in mole percentage. So now I want to know the mass composition. So what I would normally suggest is that you open an Excel file, and then you can easily convert and do the do the math. So you list all the components, and as we assume that the sum of all moles is 100 kilomole, as we have seen on the slide before, we can convert these mole percentages in moles. So 15% carbon dioxide is equal to 15 kilomoles, 25 kilomoles for water, 40 kilomoles for oxygen, and 20 kilomoles for nitrogen. And as I said, the sum is 100. Now, the next thing we have to know, or we have to look up, is the molar mass of each component. So the molar mass of carbon dioxide is 44.01 kilomoles per kilogram per kilomole. Water is 18.02 kilograms per kilomole. Oxygen is 32 kilograms per kilomole. And nitrogen is 28.02 kilogram per kilomole. Now, the next step is to multiply our moles with our molar mass, and then we would get the mass of each component. So I multiply 15 by 44.02, and then I get a mass of carbon dioxide of 660.15 kilogram. And this I do for all my components, okay? Then the next step would be to sum up, or to sum all masses of each component in order to get the mass, or the total mass, of my mixture. In this case, we will have 2,951.05 kilograms. And the last step we have to do is, in order to get our mass fractions, is I have to divide the mass of one component, and this, let's look at carbon dioxide. So I have to divide the mass of carbon dioxide, 660.15, by the total mass. So, and then I will get a mass fraction of 0.224 as a mass fraction of carbon dioxide. And again, I do this for all my components. And now, in order to check if I have done this calculation correctly, what we can do is we can sum all our mass fractions, and then I have to get 1, because as already mentioned in the slide before, the sum of all mass fractions must be 1, okay? So then we will have, as a solution for this example, is that the mixture is 22.4% of carbon dioxide, 15.3% water, 43.4% oxygen, and 18.9% nitrogen, and all expressed in mass percent. Okay, now we're going to do it the other way around, which is also pretty almost the same. So we want to convert mass to mole fractions. And again, we have a gas composed of 50% oxygen, 30% methane, and 20% nitrogen, expressed in mass percentage. And here, what we can do, we don't assume that our mixture has 100 kilomole, but we assume that our mixture has 100 kilogram, or is 100 kilogram heavy, okay? So what that means is that 50% oxygen translates to 50 kilograms oxygen, 30 kilograms methane, and 20 kilograms nitrogen. Again, we have to know our molar masses of each component. And now what we do in the next step to get our moles or kilomoles is not to multiply, but we have to divide. So we divide the mass by the molar mass. So 50 divided by 32 will get us 1.5625 kilomoles, which is the amount of kilomoles for oxygen. And this we do again for each component, okay? At the end of this step, we again sum all our kilomoles in order to get the total amount of kilomoles of our mixture, which is 4.1466 kilomoles. The next step, calculating our mole fraction. So again, for example, for oxygen, I divide the amount of kilomoles of oxygen by the total amounts of kilomoles of our mixture. So 1.5625 divided by 4.1466 will get us a mole fraction of 0.377 for oxygen. Again, I repeat this step for methane and nitrogen. And at the end, as in the example before, I can do I can sum the mole fractions and I have to get 1. So if I get 1, then I know that my calculation most probably is correct. So at the end, our mixture will be or is 37.7% oxygen, 45.1% methane, and 17.2% nitrogen, all expressed in mole percentage. Okay. Okay. Oops, sorry. Okay. So, in the next conversions, we will talk about parts per million and parts per billion and how to convert between both of them, but also some other common concentrations. So first the definition, parts per million or ppm or 10 to the power of -6, and parts per billion, parts also expressed as ppb or 10 to the power of -9, is often used to express small quantities of mole or mass fractions or even volume fractions. In order to clearly distinguish between mole, mass, and volume fractions, a suffix should be added, but sometimes it's not always added, but in order to be correct, one should always add the suffix, and the suffixes are, for mass fraction, commonly a W for weight is added as a suffix, so we would have ppmw or ppbw. For volume fractions, a V for volume is added, so we would have ppmw, no, ppmv or ppbw. The suffix V is also often used for mole fractions when we describe gas concentrations, because for gases, mole and volume are the same or are equal. When working with aqueous solutions, it is also common to use ppm or ppb, but the unit normally associated is 1 ppm is equal to 1 milligram per liter, or 1 ppb is equal to 1 microgram per liter. This is based on the assumption that the density of water is 1 gram per milliliter. Okay. Then let's do some examples. So I have a mass fraction which is 0.04, and I want to know how many parts per million weight I have. So what I have to do is simply I multiply the mass fraction 0.04 by 10 to the power of 6, which will bring me to the solution that 0.04 mass fraction is the same as 4,000 ppm weight. The same as when I want to convert mass percentage of 4%, which at the end 4% mass percentage and 0.04 mass fraction is the same, okay? So what do I have to do? I have my 4% and I want to have ppm weight. So I multiply 4 by 10 to the power of minus 2 because I have the percentage. And then again, I just multiply by 10 to the power of 6. Which, as we see, will bring us to the same solution of 40,000 ppm weight. Okay, the next example is convert volume fraction. I have a volume fraction of 0.1 and I want to know how many ppb volume I have. So I multiply 0.1 by 10 to the power of 9, which will bring us to 100 million ppb volume. Now I am given a volume percentage of 15%, and I also want to know how many ppb volume I have. So I multiply my 15% with 10 to the power of minus 2, and then again with 10 to the power of 9, and I will have at the end 150 million ppb volume. Okay, in the last step, I will show you how to convert between ppb and ppm. So I have 1,000 ppb, and I want to know how many ppm it is. So I multiply 1,000 by 10 to the power of minus 3. So this also tells us that 1,000 ppb is 1 ppm. The other way around is I want to convert 1 ppm to ppb. So I multiply 1 by 10 to the power of 3, which again tells us 1 ppm are 1,000 ppb. Okay, then let's look at some examples for aqueous solutions. So we have a solution with a concentration of 1.25 grams per liter of sodium chloride. And we want to know how much, or we want to express this concentration in ppm. So first, as we remember, we know that 1 milligram per liter is 1 ppm. So first, what we do is we convert our grams to milligrams. So 1.25 gram multiplied by 1,000 will give us milligrams. So we have 1,250 milligram per liter. So we have 1,250 milligrams per liter, and we know the conversion is 1 to 1. So we know we have 1,200 ppm, 1,250 ppm. The next example is I want to know the concentration ppb for a solution containing 0.0045 gram sodium chloride in 500 milliliter water. So we remember again that 1 microgram per liter is 1 ppb. So I convert my grams to micrograms, and the conversion factor is 1 million. So 0.0045 grams are 4,500 micrograms. Then we express our milliliters in liters divided by 1,000 liters. So we will get that, we know that 500 milliliters are 0.5 liters. We divide these two, 4,500 divided by 0.5 micrograms per liter will give us at the end a concentration of that solution of 9,000 parts per billion, ppb. Okay. The next conversion I want to talk about are normal cubic meters and standard cubic foot, and also standard cubic meters. These units are often used for gases and also normally like nitrogen when it is bought somewhere else, or if it's delivered from outside the refinery, for example. So the definition is one
Could you
normal.
repeat the last page?
Excuse. Repeat the last part.
Yeah, the last part of PPP.
Okay. PPB. This one. This one.
On the last page.
This one.
Before this one. Before this page.
Okay. This one.
Yeah.
Again. Okay. So start again. Okay. Okay, then again.
About the sodium and water, this solution.
Okay, the sodium water solution, that example. Okay, let me see. Okay, this one. Okay, I'm going to repeat this slide, okay? Correct?
Thank you. Yes, thank you.
Okay. Okay, so then again, we have aqueous solutions. We have the first example saying, or we have a solution with 1.25 grams per liter of sodium chloride. And I want to know this concentration in ppm, parts per million. So as we remember on the slide before, we've seen that 1 milligram per liter is 1 ppm. So first step, I convert my grams to milligrams by multiplying my grams by 1,000. So 1.25 grams will get us 1,250 milligrams, which ends up to, or which is then 1,250 milligrams per liter, okay, which is 1,250 ppm.
As you say, we multiply by 10 for power 1, 10 to the power of 6. If we want multiply to ppm.
Yes, that was, but not for the aqueous solutions. Because here we see, let me, I will, let us go back. Okay. Now let me go back to the other slide where we can see. No. Okay. So in the last part of the slide, you can see that the conversion factor for aqueous solution is a little bit different. You don't use the 10 power to minus 6 for ppm or 10 to the power of minus 9, but you say that 1 ppm is 1 milligram per liter. Okay, and 1 ppb is 1 microgram per liter. So here the conversion factors are a little bit different than when you convert mass fractions or mole fractions to ppm or ppb.
Okay, thank you. Just milligram and microgram. Just convert.
Correct. It's conversion factor 1-to-1 here in this case, when you talk about aqueous solutions.
Okay.
Okay.
Go ahead.
Okay, nevertheless, I'm going to then repeat the second example here, okay? So we want to express a concentration in ppb for a solution containing 0.0045 gram of sodium chloride and 500, and it's added, or let's say it's a mixture of this amount of sodium chloride and 500 milliliter of water. So as we saw, 1 ppb is 1 microgram per liter. First step, I express my grams in micrograms. So 0.0045 grams are 4,500 micrograms. Then also I express my milliliters in liters. So 500 milliliters, I divide by 1,000, bring me to 0.5 liters because let's say 1,000 milliliters is 1 liter, okay? And then I divide 4,500 by 0.5, which will get me 9,000 ppb. Okay, so the concentration of my solution of sodium chloride is 9,000 ppb. Okay, so the next conversion examples or common ones is converting between normal cubic meter, standard cubic meter and standard cubic foot, and also converting normal, let's say, absolute volumes or volume flows to these standard or normal units. So first, the definition is 1 normal cubic meter, also expressed or called, or the short form is N cubic meters, is the volume of a gas that occupies a cubic meter when the temperature is 0 degrees and the pressure is 1 atmosphere. 1 standard cubic meter, also expressed in S cubic meters, is the volume of gas that occupies a cubic meter when the temperature is 15 degrees and the pressure 1 atmosphere. 1 standard cubic foot, also expressed, or the short form is SCF, is the volume of a gas that occupies a cubic foot when the temperature is 16 degrees Fahrenheit, which in Celsius are 15.56, and the pressure is 14.696 psi absolute, which is equal also to 1 atmosphere. And converting between these three, or also converting absolute volume flows to one of these three units, the conversion is based on the ideal gas law, which is this formula, okay? Okay, then let's do some examples. Oops. Okay, so conversion. Let's convert 100 cubic meters per hour of actual volume flow at 50 degrees and a pressure of 2 atmosphere to standard cubic meters per hour. So applying the formula we saw on the slide before, which is based on the ideal gas law, we multiply our actual volume flow, 100 cubic meters per hour, by the ratio of the pressure of our actual volume flow to atmosphere divided by the pressure of the gas flow at standard cubic meters per hour, which is 1 atmosphere. Then again, we multiply that with the ratio of the temperatures expressed in Kelvin. So it is 15 degrees plus 273.15 is the temperature of our gas at standard conditions, and then divided by the temperature at 50 degrees, the temperature of our gas flow, of our actual gas flow, the 100 cubic meters per hour. And this equation will bring us to 178.34 standard cubic meters per hour. Okay. So again, so Kelvin, 0 Celsius are 273.15 Kelvin, okay? Okay, then let's do a little bit more complicated one, where we not only have to convert normal cubic meters to standard cubic foot, but also we have hours and we have day, okay? So we want to convert 5,000 normal cubic meters per hour to standard cubic foot per day. Then we apply the same formula as above. We multiply our 5,000 normal cubic meters, divide or multiplied by the ratio of the pressures of the pressure at normal cubic meter and standard cubic foot. And as we saw, they are both expressed at 1 atmosphere. So the ratio is actually 1 here. Then again, the ratio of the different temperatures is the temperature at standard cubic foot, for standard cubic foot, divided by the temperature for or at normal cubic foot, which is 0 Celsius, as you remember, and all expressed also in Kelvin. So you just sum or add 273.15. And now, how do we convert from hours to day? Oh, no. First, we also have to convert, from meters to foot. Okay. So what do? We multiply by 1, and 1 is actually, or as we saw before, we know that 1 foot are 0.3048 meters. So we have to cube that or take that into account by the power of 3. So 1 cubic meter are actually 35.3147 cubic foot. Okay. Then I express 1 hour in a day. So 1 hour is 1 divided by 24, because 1 day has 24 hours. Okay. So these are, let's say, 2 multiplication factors, which are actually 1. Yeah. Each one is, when you divide 1 by 1.24 days, is actually 1. In order to convert, the first one converts meters to foot, or cubic meters to cubic foot, and the second one will convert us hours to day. Okay. Then we multiply each term, and at the end we will get that 5,000 cubic meters per hour are 4,479,168 standard cubic foot per day. Okay.
Yes, Miss Emily, sorry.
Mhm.
There is a direct fraction factor, conversion factor between standard cubic feet and normal cubic feet, or standard
Yeah.
cubic
Okay.
meter.
Mhm.
It's 0.9. Just we multiply.
Okay. Yeah, that's easier. Yeah, that's true. Okay.
Yes, it's 0.9. Just 0.9.
Okay. Okay. I can add that as a note. 1.5. Right.
Yeah.
Good point.
It's
Thank you.
0.9. Thank you very much.
Okay. Okay, specific. Now we will look at conversion between specific gravity and API gravity. And I think 1 or 2 weeks ago, my colleague Pilar also already talked to you about or the definition of API, but just for the sake of well, just in order to repeat it again for sake of to have it complete. So the American Petroleum Institute gravity, or API gravity, is a measure of how heavy or light a petroleum liquid is compared to water. If its API gravity is greater than 10, it is lighter and floats on water. If it's less than 10, it's heavier and sinks. API is a trade association of firms engaged in all aspects of the US petroleum industry, including producers, refiners, marketers, and transporters. API gravity is thus an inverse measure of a petroleum's liquids specific gravity. It is used to compare densities of petroleum liquids. Although AP gravity is mathematical, a dimensionless quantity, it is referred to as being in degrees. So the formula to calculate AP gravity from specific gravity is AP gravity is equal to 141.5 divided by the specific gravity minus 131.5. Okay, so some examples. What is the AP gravity of water with the specific gravity of 1? So I have my formula 141.5 divided by 1 minus 131.5 is the water gravity, the AP gravity of water is 10 degrees. Now, what is the specific gravity of a light crude with an epigravity of 36 degrees? So what I have to do is I take the formula 141.5 divided by the sum of 36 plus 131.5. And I get 0.84, which tells me that light crude is lighter than water. Yeah. Because as we remember, or we will see on the next phase, also the specific gravity is always in reference to the gravity or the density, let's say, no, the density, sorry, of water, okay? So remember, oils with the low densities and hence low specific gravities have high apigravity, okay? So it's an inverse measure, or it's inverse to density. Okay. Conversion between specific gravity and density. Water has a higher density than oil. So when we pour water and oil into the same glass, oil will form the upper layer in the glass due to its smaller density. Now what we can see here in this illustration. The specific gravity is the ratio of the density of a substance to the density of a given reference substance. For liquids, the reference substance usually is water at 4 degrees and a density of 1,000 kilograms per cubic meter. The specific density of oil in reference to water is less than 1. Hence, oil is less dense than water and oil will float on water. And as we saw on the example before, the specific gravity of LNG is also less than 1, which also makes it less dense than water. And this is the formula. So the specific gravity is the density divided by the reference density, and it's normally in reference to water, the density of water. Okay. Some examples. Okay. So what is the specific gravity of ethanol at at 20 degrees and the density of ethanol at 20 degrees is 789.3 kilograms per cubic meter with reference to water at 4 degrees, and the density is for water at 4 degrees 1,000 kilograms per cubic meter. So easy calculation. You divide the density of ethanol by the density of water, and we will get 1.7893. And again, it's less than 1. So again, we know, okay, ethanol is less dense, or at 20 degrees, is less dense than water. What is the density of LNG? When we have the specific gravity at a temperature of minus 163.5 Celsius, and is equal to 0.468. with a reference to water again at 1,000 kilograms per cubic meter. So here we don't have to divide, but we have to multiply the specific gravity. So we multiply the specific gravity with the density of water, and we will get 468.1 kilograms per cubic meter for the density of LNG. Okay. So conversion between dynamic viscosity and kinematic viscosity. First, a short definition. So dynamic viscosity is the resistance of a fluid, gas or liquid, to change its shape or moving a part of the fluid relative to another part of the fluid. One can also describe it as thickness of a fluid or as the friction between the molecules when forced to move. Honey, for example, has a much higher viscosity than water. So one could see that on the left side you see water, and on the right side, well, we could say this is honey, no? And how different they move because of their viscosity, sorry. So that's the dynamic viscosity. And the kinematic viscosity is the ratio of the dynamic viscosity to its density. Okay. So the SI unit for dynamic viscosity is Newton seconds per square meter or Pascal seconds, but also one comes across a lot another unit. So it's also commonly expressed in centipoise. So 1 Newton second per square meter is 1 Pascal second, and 1 centipoise is 1 millipascal second, or 0.001 Pascal seconds, or 1.001 Newton seconds per square meter. Again, 1 poise is 100 centipoise, or 0.1 Pascal seconds, or 0.1 Newton seconds per square meters. And the same goes for, equal to the dynamic viscosity. We have something similar for the kinematic viscosity. So the SI unit for kinematic viscosity is square meters per second, but is also expressed commonly in centistrokes. So 1 centistroke is 10 to the power of -6 square meter per second, and 1 stroke are 100 centistrokes, or 10 to the power of -4 square meters per second. Okay, on the next slide, we will see some conversions, okay? And here we have to remember, for the conversion, it's important that 1 Newton are 1 kilogram meter per square second. So what is the dynamic viscosity in centipoise of water when the kinematic viscosity is 1.787 centistrokes and the density is 996.7 kilograms per square meter? So first step, I want to know the dynamic viscosity, yeah, and I have the kinematic viscosity and the density. So what I do is I multiply the kinematic viscosity with the density, yeah? And before in the next step, what I also do, I convert centistrokes to square meters seconds per seconds. And as we saw before, 1 centistroke are 10 to the power of -6 square meters per seconds. When I multiply these two factors, I will get 1.8 multiplied by 10 to the power of -3, and the unit I will get is kilograms per seconds meter. And what I now have to do is, remembering how much 1 Newton is, that I multiply again by 1 expressed in Newton and kilograms meter per square second. So 1 Newton divided by 1 kilograms meter second per square seconds is 1. And in this, by this way, I can convert this unit to Newton seconds per square meter. So I will have 1.8 multiplied by 10 to the power of minus 3 Newton seconds square meters. And now the last conversion step, I want to convert to centipoise. And again, I know that 1 centipoise are 10 to the power of minus 3 Newton seconds per square meter. And at the end, what I will get is that my dynamic viscosity of water is 1.8 centipoise. Okay, and then let's do it the other way around. I have the kinematic viscosity in centistrokes of ethanol. And what is the kinematic viscosity in centistrokes of ethanol when the dynamic viscosity is 1.2 millipascal seconds and the specific gravity is 0.7893. So when we want to have the kinematic viscosity, one has to divide the dynamic viscosity by the density. But in this case, we only have the specific gravity, but we know, okay, my density is the specific gravity multiplied by the reference density, which in this case is water. So I multiply my specific gravity by 1,000, and then I 1.2 divided by this factor. And let's see, we will, okay, sorry. And then what we also have to do is we convert the millipascal seconds to Newton seconds per square meter, which is 0.0012, or divided by 10 to the power of minus 3, okay? Oh no, or multiplied by 10 to the power of minus 3. And again, we will at the end, what we will have is 1.52 multiplied by 10 to the power of minus 6 Newton seconds meter per kilogram. So here also we have some strange unit. And in order to get to our units we want to have, or to get at the end to centistrokes, we again multiply with Newton. So we know that 1 kilogram meter per square meter per square seconds divided by 1 Newton, that's 1. So then we get our unit square meter per seconds, which are 1.52 multiplied by 10 to the power of minus 6 square meters per second. And then another conversion factor, we multiply with 1 stroke, centistroke, divided by 10 to the power of minus 6 square meters per second. Yeah, because 1 stroke is 10 to the power of minus 6 square meters per second. And then we will arrive at our solution that the kinematic viscosity of ethanol is 1. Okay. Yeah, okay, here I have to update. It's not water here, but ethanol, okay? So the kinematic viscosity is 1.52 centistrokes. Okay. Okay, conversion between joule, kilocalories, and British thermal units, also called BTU. A short refreshment on what is energy. So energy is the capacity to do work, such as the capacity to move an object by application of force or to heat up an object. Energy can exist in a variety of forms, such as electrical, mechanical, chemical, thermal, or nuclear, and can be transferred from one form to another. The SI unit of energy is joule, which is defined as the energy transferred to an object by work of moving it a distance of 1 meter against the force of 1 Newton. So we see that 1 joule is 1 Newton meter. Okay. Okay, and here we have the conversion factors. So the SI unit of energy is joule, but it commonly is also expressed in kilocalories or also BTU. So 1 kilocalorie are 4.184 kilojoules or 3.966 BTU. Then again, 1 kilojoule is 1.239 kilocalories or 0.948 BTU. Then 1 British thermal unit is 0.252 kilocalories or 1.055 kilojoules. And then with these conversion factors, let's do some examples. So how many BTU are 500 kilocalories? So we multiply our kilocalories with 3.966 and get that 500 kilocalories are 1,983 BTU. Now, how many kilojoules are 0.001 kilocalories? We multiply our kilocalories with 4.184 kilojoules and see that 4.184 multiplied by 10 to the power of minus 3 kilojoules are 0.001 kilocalories. How many kilocalories are 7 BTU? So 7 BTU multiplied by 0.252 kilocalories will get us to the conclusion that 7 BTU are 1.765 kilocalories. Okay, now we arrived at the last chapter. Okay, we will see one example for material balance and then another one for heat balance. Okay, so when you balance a steady state problem, then the most important rule for material balances is that all mass in is all mass out. So when we look at a conventional column, we say, or we see, or we can assume that the mass of the feed into the column is equal to the mass of the top product plus the mass of the bottom product. Yeah, our naming conventions will be M for mass, N for mole, and X for mass fractions. And the last one, Y for mole fractions. Okay. So our first example for the material balance. We have two streams entering the column. Yeah, stream 1 is 30% A, substance A, okay, and the rest is B. So we can say 0.3A a mass fraction, okay, and 0.7 mass fraction for B. And we call the mass of the stream 1 M1. Stream 2 is 40% A and the rest is C. So we can say 0.4A and for mass fraction and 0.6 C. And the mass for our stream 2 is M2. We have two streams exiting the column. Stream 3 is 100% A, so we can say mass fraction is 1. We call the mass of our stream 3 M3, while stream 4 is 50% B and the rest is A and C. So we know 0.5 is the mass fraction for component B, and as we know that the sum of the mass fraction for stream or mass, the mass stream M4 must be 1, so the sum of mass fraction A and mass fraction C must be 0.5. Okay. So now with this scheme, we have, let's say, translated the information we have here into a more visual scheme. And then another information we have that stream 1 is 100 kilograms per hour, and stream 2 is 1,000 kilograms per hour. And now we can solve the mass balance. We also assume that the percentages given here are mass percentages, okay? So with this information, with this scheme, what we can do is we can elaborate the mass balance for each component, okay? So for component A, we know that 0.3, yeah, mass fraction of the whole mass of mass 1, 0.4 plus 0.4 multiplied by the whole mass of stream 2. Then we know that stream 3, the 100%, it was 100% A, so we can write 1 multiplied by the mass of stream 3. And then we didn't know the mass fraction of A in stream 4. So what we do is we write XA multiplied by M4. And we do this for the other two components as well. And when we have elaborated the balances for each component, what we can also do as a step in order to check if we did these three equations correctly, we can sum them up, okay? So for example, 0.3 plus 0.7 plus 0 for mass 1, stream mass 1 is 1. And we do that for the other mass streams as well. So what we, at the end, what we will have to have is mass 1 and mass 2 are equal to mass 3 and mass 4, which we see is the fundamental assumption we do is that all mass entering the column or a system is equal to the mass exiting. And we know that we have 3 unknowns in our mass balance, is M3, M4, and mass fraction of A. So we have 3 equations and 3 unknowns, so we know we can solve our problem. So we start and solve our equations. So we look at the 3 mass balances or mass equations and look, of course, we do the first one where we have just one unknown. Okay, so we can do the B mass balance of B first. So we know that M1 is 1,000 kilograms per hour. So then we can conclude or solve this equation for the component B and know that the mass 4 or the mass of the stream 4 is 1,400 kilograms per hour. Then we look at the equation for the component C and can solve the mass fraction for A. So the mass fraction for A is then XA equal to 0.07. And then at the end, we just have the last one to solve, which is for the component A. And we will get a mass for stream 3 of 600 kilograms per hour. Now again, we can check in the last step that we did the calculations correctly and sum all the masses. So at the beginning of our, or in the we already had given the mass of the M1 and M2 streams, so 1,000 kilograms per hour plus 1,000 kilograms per hour. And now in our 2 equations, we've solved that stream 3 is 600 kilograms per hour and stream 4 is 1,400 kilograms per hour. And if we sum them, we see, okay, here we have 2,000 and here again we have 2,000, so it's correct. Okay, then For the last few slides, we will look at a heat balance example. And the most common one is also a heat exchanger. So we assume we have a heat exchanger with hot hydrogen entering the heat exchanger with 100 degrees, and it's cooled by cooling water on the other side of the heat exchanger, entering at 30 degrees Celsius and exiting at 35 degrees. The mass flow of the cooling water is 500 kilograms per hour, and the one of hydrogen is 100 kilograms per hour. In order to solve this problem, we also have to know the heat capacity. So the heat capacity of water is 4.186 kilojoule per kilogram Kelvin, and the one of hydrogen is 14.3 kilojoules per kilogram. Remember that the heat capacity is a physical property of matter, defined as the amount of energy that must be added in form of heat to 1 unit of mass of a substance in order to cause an increase in temperature. What we can do again now is draw a scheme which visualizes our problem in a better way. So we always have a hot and a cold side in a heat exchanger. No material is exchanged in this in a heat exchanger normally, okay? Or no. And just energy is exchanged, okay? And the energy is called Q. We also assume for this problem that all energy from hydrogen is transferred to cooling water without losses, okay? That, of course, in reality never happens, but for this equation, we will assume. We also assume that we don't have any pressure losses, yeah? Because normally the heat capacity is dependent on not only temperature but also on pressure, but we will assume we have no pressure losses within our heat exchanger. So we can assume that the heat capacities are constant. And as I said, temperature is also a factor for heat capacity, or is dependent. A function, the heat capacity is a function of temperature, but it's insignificant. So normally the heat capacities don't change a lot with changing, with increasing or decreasing temperature. So we can also assume that the heat capacity is constant. Okay, so then we draw our scheme, and what we see is that we have one unknown, which of course is what we want to know is the outlet temperature of hydrogen. Sorry. So with what temperature does the hydrogen exit the heat exchanger? And we want to know what heat is exchanged, okay, Q. So for the heat exchange, we have a very simple equation. So the heat exchange is the heat capacity of water multiplied by the delta T, which is the difference between inlet and outlet temperature, and the mass of water. And as we said, that the heat exchanged, or all the heat that is all the heat exiting, let's say the stream of hydrogen goes into the stream of water, and the energy of water, or the expressed in temperature rise in the water stream. So we can say that also the heat capacity of hydrogen multiplied by the temperature difference of hydrogen in an outlet multiplied by mass is equal to the same multiplication for water, okay? So then we do the math, and we change the formula in order to have the outlet temperature of hydrogen at the end, which we can say is 100 Celsius minus 4.186 kilojoule per kilogram multiplied by 5 Celsius, which is the temperature difference of water inlet and outlet, multiplied by the mass, the mass flow of water, divided by the heat capacity of hydrogen, divided by the mass of hydrogen. So then at the end we get 100 degrees, which is the temperature at the inlet of for hydrogen, minus 7.3, and we will get 92.7 degrees. So our hydrogen flow will exit the heat exchanger at 92.7 degrees. So now the last thing we wanted to know is how much heat is exchanged. And we can either calculate it with the water side, but we could also use the hydrogen side, as we also now know the exiting temperature of the hydrogen. But in this case, we will take the water side. So the heat exchange is the heat capacity multiplied by the temperature difference of water at inlet and outlet, multiplied by the mass flow of water, and we will get at the end 10,465 kilojoule per hour. Yeah, okay, and that's the equation again. And maybe just one note. So delta T, normally when you look at the books, it's expressed in Kelvin, but as it's the difference, you can also use degrees Celsius, okay? So yeah, that's all from my side. Ahmed, if you want to
Thank you
ask
so much.
the attendings if they have any questions.
Yeah, thanks, Anneli. Thanks for your time and your effort. Thanks. Guys, ladies and gentlemen, if you have any questions, please can you let us know? Either you raise your hand using the Zoom application, or you send it in the chat. So it's up to you. شباب أحد عنده سؤال؟ I don't see any questions raised so far. Okay. Let's check the chat. No questions. Okay. Okay. I don't see any questions, so it's okay. I hope that it's understandable for all the attendees today.
Yeah.
Okay. So let's see.